Let me settle the problem. Yes. Mhm. Hello. Are you hearing me? Okay, Dr. Normi. How about screen? My slides? Okay, thank you. In that case, let us start it. Today's topic for discussion is Lie and the Lode algebras. Lie and Lode algebras. In fact, I uploaded 50 slides in WhatsApp and the Telegram group for this week, 2 sessions, today and Thursday sessions. Then I will try go through all the slides. If can manage, no problem. If cannot, then you can go through that and do it yourself. And any question, then you can just send me a message asking some questions related to that topics there in my slides. Okay. All right. So let us now go that things which we would have discussed last time. We discussed algebras and some classes of algebras. The first is associative algebra. We have seen any associative algebra is alternative algebra. Any Lie algebra is multiple algebra. And the Lie algebra is Leibniz algebra. And the Leibniz algebra A is a Lie algebra under this condition, the anti-commutativity condition. So we concluded that the intersection of classes of multiple algebras and the Leibniz algebras is exactly the class of Lie algebras. So Lie algebras is inside of multiple and the Leibniz algebras. And we came to the following so-called minus operation. First of all, we define what's a commutator. The commutator in algebra A is such a bilinear function. xy, comma y is x times y minus y times x. So this is, in fact, bilinear function. that means it is linear with respect to x and linear with respect to y. It can be easily seen from the definition. Let me start to annotate here. Okay, so I have x, xy is xy minus yx. If I substitute here alpha x plus beta, let me take x1, beta x2 to y, this square bracket, and this is just take this x replaced by this guy, this x also replaced by this. So I will get alpha x1 plus beta x2 times y minus y times alpha x1 plus beta x2. But this product operation is bilinear. Here also this one bilinear product. This is in algebra A. You will get these product operations. So that's why you can just expand, just opening the brackets, this one and that one. So you will get alpha x1y plus beta x2y minus alpha yx1 minus beta yx2. I should keep the order of multipliers, factors, because algebra is not commutative. So it equals, just I will factor out alpha from these two. So I will get alpha here x1y minus yx1, then plus beta. If I factor out from these two, I will get x2y minus yx2. So that means I have alpha, but this guy is, according to this definition, is square bracket of x1 y. This bracket, this is beta and x2y. So that means this bilinear function is linear with respect to first argument. The same can be done with respect to second. Similar way. So that's why this is a bilinear function, bilinear operation. Let us go to, so this is bilinear. Now, of course, you can consider this algebra now, algebra A, with respect to this bilinear function. So you may consider A, this A. This A and this bracket. since this is bilinear, so you will get algebra. So that algebra A with respect to this operation is called A minus algebra. A minus algebra. This A minus. So that means this algebra with this bilinear operation. Algebraic operation. Product operation is given as a bracket. X, comma, Y in square brackets. So that is a multiplication. So that algebra we denote as a minus. Now, there is such a theorem. Birkhoff-Poincaré-Birkhoff theorem for Lie algebras. Now we'll consider this A as a Lie algebra. Then this theorem says every Lie algebra is isomorphic to a subalgebra of A minus, where A is associative algebra. So that means if you consider an associative algebra A, some associative algebra A is a dot operation. So that means you have vector space V. On that vector space, you have dot operation. With respect to that dot operation, you have an algebra A, but this product satisfies associativity condition X times Y times G is X times YZ. Later we will see class of associative algebras separately. So then, if we denote xy, the above function here, as x dot y minus y dot x, then the resulting algebra will be minus algebra for this associative algebra. This is minus algebra. The claim of this theorem is any Lie algebra can be considered as a subalgebra of this. In fact, A minus algebra is a Lie algebra. A minus is a Lie algebra. Any finite dimensional algebra, Lie algebra, can be considered as a subalgebra of this A minus algebra, where A is associative algebra. Associative algebra. So this is a Poincaré-Birkhoff theorem for Lie algebras. Okay, now if A is alternative algebra, then A minus is a Maltsev algebra. Maltsev algebra. Now we will introduce another operation, so-called plus operation or plus algebra, which is x times y plus y times x times 1 over 2. Of course, characteristic of the field where this algebra is given is not 2. Otherwise, we cannot divide by 2. So characteristic is not 2. So new operation, this time this operation we will denote as a x circle y. X circle y. Then easy to check, this also bilinear function. Linear with respect to x, and it is linear with respect to y. What can be easily seen again, just replacing x by alpha x1 plus beta x2, substitute here, substitute, and just open the brackets and regroup again. So you will get bilinearity as already I've demonstrated above. Okay. Now, if A is an alternative algebra, then that algebra with this product, which is we denote as A plus, is a Jordan algebra. So a Jordan algebra is called spatial Jordan algebra if it is isomorphic to a subalgebra of A plus for some associative algebra A. Otherwise, Jordan algebra is called exceptional. Here is a statement that the analog of Poincaré-Birkhoff theorem for Jordan algebras is false. Not every Jordan algebra is spatial, because for Lie algebra, we can get statement that any Lie algebra is spatial. But for Jordan algebra's case, it is wrong. Not every Jordan algebra is a spatial algebra. So there are exceptional algebras also. Here some such an example. AB algebra was an involution I. So if we take subset of this algebra, which the set is called the set of all symmetric elements, where I is A, all symmetric parts. It is closed with respect to Jordan bracket. So this is a Jordan algebra. So now, if A is associative algebra, then this algebra and this associative is spatial Jordan algebra. If I take as A matrices, 3 by 3 Hermitian matrices, and as a involution, I will take conjugation operation. Then H of O3 is an example of exceptional simple Jordan algebra, just exceptional Jordan algebra. So here, example of spatial Jordan algebra, and here this is an example of exceptional Jordan algebra. Okay, now simplicity. We will come for simplicity some specific class of algebras later on, but here is general definition of simplicity. An algebra A is simple if product A by itself is not trivial, and A has only two ideals, 0 and A itself. So what does it mean? This means a span of, let me write it, this one is span of elements of the following form. X, Y, span of, let me take summation. Summation is finite. Xi, yi. X and Y, they are Xi and Yi, they are elements of A. This is given by this, okay? Because it should be subspace. This is an ideal. This is ideal. So what does it mean? If this is an ideal and it is not 0, it's not 0, then it must be just algebra itself. Algebra itself. It is from this definition can be obtained. So if you have simple algebra, then product of algebra by itself is just algebra itself. Okay, an algebra is semi-simple if it is direct sum of simple algebras. So semi-direct means semi-simple means you have algebra A, then you will get A1 plus A2 etc. plus AN, where NI or AI, sorry, AI is a simple algebra. So algebra is semi-simple if it is written as a direct sum of simple certain copies of simple algebras. Okay, now nilpotency solubility. Let us consider algebra A. Denote A sub A upper 1 this way and this way. For 1 we'll take algebra itself, and by induction we'll define such a series. An plus 1 is such a summation ai times j. So ai, because I can multiply by a itself. If I multiply it I times, I will get this, and multiply j times, I will get this, and I will take span of this subset of A. So that is, I will denote this A n plus 1. If I get, in this case, A, because 1 is given, for 2, what how I define it? So 1 times 1 is 2. If it is 2, then I will get 3 is a to the 2 times a to the 2. If n is 3, then a to the 3 is a to the 4, etc. etc. So this is by induction define some series of subsets. In fact, they are ideals. This is an ideal. This also is an ideal of A. So now there is a definition. Algebra A is called nilpotent if there exists K such that that series of these ideals terminates at 0. So because each time what you will get as a result, you will get the biggest one A1, the biggest one A1, and it is inside because subset of that is A2, subset of A3, etc. So you have such a inclusions. In fact, somewhere you can get just equality, and the further you will get only equalities. In that case, algebra is not nilpotent. If it is nilpotent, if this series comes to 0. So last term, say a to the k minus 1, and here ak, which is 0. Decreasing, decreasing, decreasing. If you come to 0, then A is called nilpotent algebra. Nilpotent. So that is K here, there exists k such that a to the k is 0. Of course, further terms will be 0. An algebra is called solvable if there exists S such that this series of ideals terminates, comes to 0. So you will get A, 1 first, then A, 2, etc. Here you will get some A, S plus 1, see, S minus 1, sorry. Here you will get AS. If this AS is 0, decreasing comes to 0, then that algebra A is called solvable algebra. So this is a difference between important and solvable algebras. The smallest natural such a K, respectively S, so properties above is called nilpotency index or solubility index. So that means all previous are non-zero. Only this one is a to the k is 0. A to the k minus 1, k minus 2, etc. They are not 0. So last 0, you will pick up this k in the, we call that index of nilpotency. Here also S is called index of solvability. Okay, so now just now we have seen if algebra is simple, of course product by itself is algebra itself. Why? Because to be simple, this shouldn't be 0, because since algebra has only 2 ideals, it may be 0 or whole entire that algebra A. So a second case must happen. If algebra is nilpotent of index of nilpotency k, then product of all any k elements with any arrangement of parentheses equals 0. And there exists some product which is not 0 with the k minus 1 factors. So that is a nilpotency. So in any nilpotent algebra is solvable, but the converse is not true in general. We will see in example of Lie algebras this statement. So any solvable associative algebra is nilpotent. So that means nilpotency and the solubility for associative algebras are the same, because here it is based on the second claim. Okay, now derivation algebra, very important invariant of algebra. A linear transformation D from A to A is said to be derivation of algebra A if d lambda xy is lambda dxy plus lambda x dy. If you write lambda, just lambda xy as xy, as usual xy, then this is exactly Leibniz rule, because you will get d of xy equals dxy plus x dy. I want to draw your attention that you cannot change the order. You should keep the order x, y. So x first, then y, must be kept everywhere. You cannot switch them because algebra is not commutative. If it is commutative, you can do it, but since it's not commutative, you cannot do it. So you should write as it is. Okay, so proposition. They said, now we will consider some algebra A, and the set of all such a linear transformation satisfying this condition. We will collect them and denote them dear A, dear A. So that is some set of some functions given on A, from A into A, satisfying this Leibniz rule. Denote by dear A. Now, of course, if you have two such a function, then you can take their compositions, because you have A here, A, and A. This is one of them, D1. This is another one, D2. You can compose them. If you compose, you will get such a function. This function is called D2 or D1. First apply D1, then apply D2. So you, from here, if you apply D1, you will come here. Applying then D2, you will get here. So for each element of A, you assign another element of A again. So that's this is a function from A into A. Now you may ask question, if this D1 and D2 satisfy this condition, can I say D2 or D1 or D1 or D2 also satisfy that or not? You can check it. No. D1 or D2. So that means if D1 and the D2 are derivations, then their composite is not derivation. General. This composition is not, these two compositions, they are not derivations. But you should find some remedy. Remedy comes as follows. So this is not derivative, this is not derivation, this is also not derivation. So you can consider their difference, D1 or D2 minus D2 or D1. So resulting function, because this is bilinear function, composite is by another bilinear function, result is bilinear function. These two also bilinear functions, linear functions. Linear functions here, composite of linear functions will be linear function. Composite here, two linear functions here, linear function again. So difference of two linear function is a linear function. This is a linear function, first of all. Linear function. Then this proposition says this is not only linear function from A to A. In fact, this one is linear function from A to A. But they say it is not only linear function from A to A. It is a derivation. Result, if you compose this, take difference of compositions. If you denote it as bracket D1, D2, then with respect to this bracket, Here A is an algebra. This will be a bilinear function, that algebra. So we need to prove this is a derivative. It is the derivation. It satisfies the Leibniz rule. Here is a proof of that. By the way, this is a linearity. Here, now why that is derivative? What we'll do for that? D1, D2 of this product is difference of compositions. Difference of compositions, just you can write composition of this product minus this composition applied to this product. But here, see, this according to definition, this one D1, D2 applied to this, but D2 is a derivation. So that's why I can write lambda D2 xy plus lambda x D2y because of this is derivative. This is a Leibniz rule. D2 is derivation. D2 is derivation. Here written because D1 is derivation. D1 is derivation. Okay, now just apply D2, D1. Once you apply D1, D1 also is a derivation. So the way each time you apply D1 to D2, lambda times this, then this times the D1 of this, which is given here, split into this. D1 applied to this, you have two terms. Then D1 applied to this, you have another two terms. Minus D2 applied to this, you have two terms. And the D2 applied to this, you have another two terms. Now you can regroup. Just taking here, say lambda D2 D1. Here lambda. You can write this lambda D1 or D2 minus D2 or D1 xy. And lambda x times D1 or D2 minus D2 or D1 y. But this guy is bracket of D1 D2. This guy is bracket D1 D2. So that's why number yeah. So you will get derivative that Leibniz rule. This applying to this is D1 applied to this D1 and the plus this applied to D2, what is given here. Lambda D1 applied to the x times y plus lambda x times D1 D2 y. This is exactly Leibniz rule. So that's why D1 bracket D1 D2 is a derivation. So bilinear function is given. This bilinear function. Because with respect to D1 and D2 now. Bilinear function, let me read bilinear. Bilinear function. So on algebra A is given such a bilinear function with respect to D1, D2 in this algebra. On this algebra. In algebra A, it is linear function, but with respect to D1, D2, it is bilinear function. Bilinear function here. Bilinear function in dir A. Let me write here. In dir A. So vector space, and this bilinear operation is given. This bilinear operation is derivation. So that's why this is algebra. This is with respect to this Lie algebra. Let me skip it. Why it is Lie algebra, we will see later on when we come to Lie algebra definition. Let us now discuss each class of algebra separately. So let us discuss associative algebra. We start to discuss it. So our associative algebra is algebra with a product operation dot satisfying this condition, this axiom. A times B times C is A times BC. So this is our associative algebra. Examples of associative algebras. Here, let me first examples. Complex numbers, algebra, product operation is given there. Product operation is associative. It is algebra over R. Two-dimensional algebra. If over Q, C is infinite dimensional algebra. Over R is two-dimensional because we have linearly as a vector space, two-dimensional, because you have two vectors here, which is linearly independent, and complex numbers is spanned by that two vectors. One vector is 1, another vector is I. So 1, 2 vectors. Any complex number, if you remember, this is written as A plus BI. So that means this is just A times 1 plus B times A times E1, B times I. Or it is A times E1 plus B times E2. Where A, B are real numbers. So complex numbers, two-dimensional algebra over real numbers. Over rational numbers, of course, it is infinite dimensional algebra, because this is infinite dimensional vector space over Q. N by N square matrices with from entries from some field F. Associative algebra, dimension of that algebra is N squared, because you can find N squared linearly dependent elements. They are EIJ. This is matrices. Entries on intersection I's row and the J's column is 1. Beyond, any elements are 0. This is I's row. This is J's column. Here we will get 1. So I's row 1 and J's column. J's column 1. All other entries are 0. So that is sometimes called matrix units for this n by n matrices. Okay, next one is endomorphisms of a vector space over a field F. If vector space V is n-dimensional, then this n-squared dimensional associative algebra. You have to define product operation. That is, vector space is clear. In fact, this is isomorphic to this, because here is n-squared dimensional here also n-squared dimensional. Any two n-squared dimensional vector space are the same, because they are isomorphic already. We have seen it. So how to introduce product operation here? You have one operation. Endomorphism means linear transformations, V into V. If you have F1 here, F2, then you may consider its composition. F is a composite of these two, F1 or F2, F2 or F1, or F1 or F2, doesn't matter. So then, with respect to this operation, this you can take as a product operation in endomorphisms. So with respect to this operation, it is algebra. This operation is associative because composition operation is associative. So this is associative algebra. Polynomials with the coefficients from a field F also associative algebra. Addition and the multiplication by scalar is given there because it is vector space. By the way, it's a vector space over F. Polynomials has infinite dimension. So infinite dimensional algebra, infinite dimensional vector space. So how to introduce product? Product is just a product of polynomials. Already have seen a product of polynomials in rings. We can, when we studied rings, it was A0 plus B0, A0 times B0 plus A0 B1 plus A0 B1 plus A1 B0 x squared, or just x, plus etc. So coefficients, if you remember, you can find by using some summation. So result of product of two such a polynomial is a polynomial again if ai and the bj from f, then under these combinations also you will get element of f. So resulting polynomial with coefficients from f. But this product operation is associative. It is usual product operation, just you can take another h and multiply, your result will be some polynomial, and you compare them with that multiplying f of x to g and h. So result will be the same. So that's why this is an example of associative algebra. Okay, now examples of some important associative algebras. Here, by the way, let me go to this point. We have associativity condition here. We can consider this condition, associative condition, we can just go to basis level and define associative algebra as follows. An algebra is associative if and only if EI times EJ times EK is EI times EJ times EK. So associativity you can demand from for basis vectors if algebra is n-dimensional. If you have n-dimensional associative algebra, then you can take basis of that and check associativity for that basis vectors. It is enough to be for algebra to be entire algebra to be associative. How to get it? Just you should write if for any basis vector you have this, then easy to get why this condition holds, because by linearity you just take basis vectors, expand basis vectors here, basis vectors with respect to this basis, and compare coefficients of basis vector from this side and from this side. You will get from here to here condition. So this condition, this axiom is equivalent to this axiom. If you have associative algebra, you have basis to verify for algebra A to be associative, or any algebra C, more precise. If you have an algebra, then you want to prove, you want to check that to be associative. Not necessary to verify for any its elements associated with condition this. Just take its n basis vectors, and for basis vectors you can verify this condition. If this condition holds for basis vector, then algebra is associative algebra. Okay, now examples of associative algebras. In our last class, if you remember, we already discussed to give algebra, it is enough to give structure constants for algebra. So that's why here is that way are followed. That way is followed. So smart. You see you here. So here gamma 1 1 2 is 1. All other structure constants are 0. Because here 1 1 with respect to that basis you expand, then coefficient of basis vector 2 is 1, others 0, coefficient E1 is 0. So that's why for this algebra structure constant is gamma 1 1 2 is 1, all others they are 4. So one of them is 1, others 0, 3 is 0, 3 are 0. Okay, here this is two-dimensional, by the way, two-dimensional associative algebra. Here, three-dimensional associative algebra. Here also you can see how many structure constants here. Of course, 3 cube, because three-dimensional vector space cube. So must be 27 numbers. 27 numbers. Only one is given. Oh, others also is given. Only one of them is non-zero, 1. So gamma 1 1, or gamma 1 1 2, sorry, is 1. All others 0. All others are 0. Okay, how about here? Here is given without squares. Of course, again you will get 27. Alpha is not square. It's not square of another element of f. So here is given gamma 1 1. 3 is alpha. Gamma 2 2 3 is 1. Others 0. In fact, here you have infinitely many associative algebras if f is an infinite field. If f is finite field, then of course you will get only finite number associative algebras. The same here, you can see gamma 113 is alpha, gamma 223 is 1, gamma 213 is 1, and alpha is any non-zero element. By the way, star means non-zero element of the field F. Here, gamma 123 is 1, gamma 21, 3 is minus 1. This is interesting. So gamma 123 is 1, and gamma 213 is minus 1. Add 0. The rest 0 here. Here, gamma 112 is 1, gamma 123. So 123 is 1, and gamma 213 is also 1, etc. So these are a list of associative algebras in dimension 2, dimension 3. Okay, now if you remember, our main problem is how to get associative algebra. Associative algebras, we can classify up to isomorphism. Or isomorphism means two algebras can be considered, can be identified. Here, by the way, look at this. This means in dimension 2, you have only one non-trivial associative algebra. All other associative algebras are can be identified by this algebra. In dimension 3, 1, 2, 3, 4, 5, 6 non-trivial associative algebras, classes of course. But here, due to this alpha, you have infinitely many here and infinitely many here, if F is infinite field. So that's why in general you have infinitely many algebras, but these 6 algebras are not isomorphic to each other. Then for different values of alpha from this class, they are also not isomorphic to each other. These also. So for different values of alpha, you have different associative algebras. Overall, you have infinitely many associative algebras in dimension 3, provided that your field is has infinitely many elements. Now, there is a fundamental theorem given by Wedderburn and Aten. Any finite dimensional, please pay attention, finite dimensional semi-simple associative algebra is uniquely decomposed into direct sum of simple algebras. What does it mean, semi-simple? Simple means such as simple algebras. So A is semi-simple, it can be written as a direct sum of simple. So what is simplicity? Simplicity means it has no non-trivial two-sided ideals. But any simple associative algebra can be described as follows by this theorem. Any finite dimensional simple associative algebra A is isomorphic to the algebra of matrices, n by n matrices, over a division ring or skew field. Do you remember one of the examples of skew field is it was quaternions. So any finite dimensional simple associative algebra is given as a matrix form, but entries of that matrices from some division ring or square field. Now, that n, this n, and this division ring, they are uniquely determined by the algebra A. So if you have algebra, you will find n and the d, and this algebra will be isomorphic to this matrix algebra. So that's why for associative algebra, structure of associative algebras more and less clear for semi-simple case. So semi-simple case is written as a finite direct sum of simple, but simple algebras is given by this theorem as a matrix algebras. So that's why semi-simple case is completely classified. How about not semi-simple case? Here is given some information on classification. Semi-simple case is given, but not semi-simple case is not fully solved yet, even over algebraically closed field. Some attempts have been given by Pierce, and for 3, 4, 5 dimensions by Scorza, Gabriel, and Mazzola. There are some papers on classification of associative algebra, but they are unitary. That means associative algebra with unit elements. So 3-dimensional, 4-dimensional, 5-dimensional cases. Okay, next class of algebras are Lie algebras. Many things on algebras, Lie algebras already we know. So first of all, antisymmetricity. So any Lie algebra is antisymmetric. X is 0, or xy is minus yx. Then that algebra product satisfied is a Jacobi identity. Last time we discussed it. This is Jacobi identity. It can be written as a right or left multiplication operator, which is a differentiation. If you write dz, last class we discussed it. So if you take and dzx as a xz, then this Jacobi identity means dzxy is dzx times y plus x times dgy. So this Jacobi identity is equivalent for this right multiplication operator to be derivation. So you can define Lie algebra as follows. So Lie algebra is a algebra, anti-commutative algebra or antisymmetric algebra, such that left or right multiplication operators are derivations, because Jacobi identity is equivalent to this. Okay, let us consider some examples. So 3-dimensional real space, 2 vectors. You can define product of these 2 vectors as given here. In fact, this product is cross product of these two vectors. Cross product. You know cross product, right? This is a IGK. Here x1, x2, x, or x1, x2, x3. And here y1, y2, y3. This is a cross product x and y. So cross product, with respect to cross product, three-dimensional vector space is in the algebra. Why it is antisymmetric? Because if you change rows, this determinant becomes minus this determinant. So that's why anti-commutative. Jacobi identity, of course, you should make some calculations. Check it. So the Jacobi identity is also false. Okay, now that minus operation, by the way, if you have associative algebra, then minus of associative algebra is the Lie algebra. It is exactly A minus. This because this operation is minus algebra operation. So particularly endomorphisms of vector space is a Lie algebra with respect to this. For endomorphism, you have composition operation, composition. So the difference of compositions give this. That algebra is algebra Lie. It is denoted GLVF or GLV. Okay, so if A is matrix algebra, then it is denoted GL and F. You see, in this general case, endomorphisms case, here matrices case, notations are different. GL and F. Here GLV or GLVF. Only for matrices case, because n by n matrices with the entries in F, it is associative algebra. If you, with respect to this associative algebra, consider this bracket, then this becomes Lie algebra. That Lie algebra is denoted GL and F or GL and this way. Sometimes these notations, the notation also used. Okay. All right. And now, ideals in Lie algebra. The subspace of Lie algebra is said to be an ideal if, as usual, product with respect to that bracket operation. That Lie algebra operation would denote as a bracket. So this is lambda xy. So result of lambda xy in I again. But in Lie algebra, you have interesting phenomena because it is antisymmetric. So any left ideal is right ideal. So that's why Lie algebra has only two-sided ideals. It doesn't have one-sided. All ideals are two-sided ideals. Here are some examples of ideals in Lie algebras. If you have Lie algebra L, its center, by the way, for Lie algebra, center is defined this way. For other cases, for associative algebra, center is defined by another way. If you have associative algebra A, then its center is those elements of A such that x times y equals y times x for any y from A. Can you see the difference? Why center is defined this way? It makes sense. Why? Because of this. Because of this. So x and y product 0 means xy equals yx. Center means in associative algebra, center must go to the algebra center. So that's why if you consider associative algebra A and you take minus algebra, then it will be the algebra. So this center comes to the center of the algebra. So that's why center is defined this way. xy is 0 for all y from L. In fact, the center for other cases defined this way. Since between A associative algebras and Lie algebras there is some minus operation. So for Lie algebras we have to define center this way. Okay, derived algebra. We can multiply Lie algebra by itself with respect to that bracket operation. So that is span of xy, where x and y from L. Already in general case I have written this today. So L times L is span xy with respect to this bracket operation, of course. It is an ideal. Why it is an ideal? Because this ideal is clear, right? Because if you multiply, since it is 0, if you multiply by anything, result will be 0 again. So that's why center is an ideal. Why this is an ideal? Because this is from Jacob identity. You will get from Jacob identity. You can obtain it. You multiplying. If say x from the here, multiplying from left and right side, you will get element of this form. You can get. By the way, it's given as a span. Span means finite number linear combination of elements of this form. Just multiply from left side and right side, you will get element of this form again. So you can check it easily. Now more. So here you multiply L by itself. In fact, you can multiply by L taking its case power. L to the K and L. If L is 1, you will get this span. If L is 2, because L is 2, you will get this. You should multiply it by L. If L is 3, resulting, you should multiply by L, etc. So result, you will get such a series of ideals again. If this is an ideal, then this also is ideal, you can see. Another series of ideal is given by this rule. In general, for algebras case, we already have discussed it. And now this is called derived series. This central series, this is a derived series. First one is called central series. Second one is called derived series. We already discussed this. These inclusions and these inclusions. Now you can easy to see L to the this way power I is inside of L to the 2 to the I minus 1 in this form power. So that's why if you look at the usual nilpotent solubility, if this terminates to 0, then L we will call nilpotent. If this goes to 0, then L we will call soluble. Since somewhere here you will get inclusion here, correct or not? You will get inclusion. This includes L to the 2I minus 1. If this terminates, its result goes to 0, so that means it goes to 0. So that means this series also must go to 0, because terms of these inclusions are inside of the terms of these inclusions. If this goes to 0, this definitely will go 0. So that's why any nilpotent algebra is soluble. Not soluble is not nilpotent. Soluble algebra is not nilpotent. From termination of this series, you cannot get termination of this. From this, you can get this, but the converse is not true. Here also the same. In that case, index of nilpotency and the index of solubility. So soluble if it is nilpotent if it is 0, soluble if it is 0, and the minimal one is called index of nilpotency, index of solubility. Okay, now this is a lemma here. Let me discuss this lemma. Maybe it will be last what I'm going to say today. If L is a Lie algebra, the I and the J they are its ideals. Then if L is soluble, so are all subalgebras in the homomorphic image of L. They are soluble. If I is soluble and L over I also is soluble, then L is soluble. If you have two soluble ideals, then their sum also is soluble. So that's adding soluble parts of a Lie algebra. You will get maximal with respect to inclusion, a soluble ideal like this. You will add I, J, then another soluble ideal, add, etc., etc. So you will get some maximal soluble ideal. That's maximal soluble ideal is called a radical of Lie algebra L. It will play important role in study of structure of algebra L. That we will discuss maybe next class. Any questions, please? Hello? Hello, are you around there?
No question.
Okay. If no question, thank you.
Isamiddin aka.
Laba Haydar aka.
Isamiddin aka, 3 ta magistrni anılarını tashladim. Rezyume